We're going to look at complex circuits now. So this is in your notes, the backtracking, because you remember we skipped this the other night. So for complex circuits, all that is, it's complex or compound. It means that you've got both series and parallel resistors. So instead of just straight series or straight parallel, you have a combination of the both of them. And we want to be able to analyze more complex circuits such as this one. So here's a picture of, you've got parallel, but then you've also got parallel in with series, and it's just a whole big mess of wires. So there's two rules that you need to know. In every loop, the sum of the voltage across the resistors equals the voltage of this power supply. So a loop is like, that's a loop, this is a loop, here's your battery. So it's a little bit complicated because you've got that. But in other words, the sum of the voltage in every loop should equal the voltage of the power supply. And this will make perfect sense, hopefully, once we look at this in examples with concrete examples. So voltage has to add up. Current splits when coming to a junction. So the total current going into a junction, and this is a junction. So junction, junction, junction. A junction is wherever the wires are splitting. So if your wire splits, your current splits. So a current splits when coming into a junction. The total current going in must equal the total going out. When resistors are one after another, the current must be the same through both of them. So in other words, resistors that are in series will have the same current. So the current here equals the current here, which equals the current here. And the voltage, so the total voltage would equal the voltage here plus the voltage here plus the voltage here. And that's pretty much all you need to know in terms of voltage and current for the basic rules. And then when we apply this with resistors, you'll see how it works. So let's do the two practice problems just using the rules that we know. So again, voltage needs to add up to the total voltage of the power supply. Current needs to split when you get to a junction, but you're also adding it up. So practice. Let me move this a little bit. For the first one, we're looking for the missing voltages, and voltage has to add up to your total across each loop. We have a 30 volt battery. There's 4 volts this resistor, so we're looking for this resistor. It gives us 11 volts here, we need to know what that is, 6 volts here, we need to know what that is, and 17 volts. Voltage for parallel resistors is equal. So in other words, this is 17, these need to add up to 17, and these need to add up to 17. So 17 minus 6, this is 11 volts. This is 6 volts. Again, how do I know that? Because for in parallel, resistors in parallel are going to have equal voltage. So you have 17 here. This resistor is in parallel with these two, which is in parallel with these two. So then we have a loop that needs to add up to 30. 6 volts plus 11 volts is 17. 17 plus 4 is 21. 21 plus 9 volts gets you 30. And that's all you have to do. So now for the next one, looking for the missing currents. Currents add up as you go into junctions. So splitting a junction, you're going to add the currents. And we also know that currents in series are going to be equal. So in other words, for resistors that are in series, you'll have the same current. So this is easy. These two are in series, means that that also has to be 5 amps. These two are in series, so that's 3 amps. And these two are in series, that's 11 amps. That's it. So 11 amps going in. It doesn't ask for this last one over here, but let's solve it anyway. We have 11 amps going into this junction. It splits into 3 plus 5, which is 8, which means that this last one has to be 3 amps. Because 3 plus 3 is 6 plus 5 is 11 amps. So that's how it works in terms of splitting the current in junctions and making sure that current is the same across series resistors. Let's skip over now to a couple pages where it says resistance in complex circuits. We'll look at that one and then do the practice, and then that's it. We'll start putting this all together tomorrow with lots and lots and lots of practice on figuring these out. Now we want to look at resistance in complex circuits, and then the next problem we'll put everything together with resistance, current, and voltage. But here let's look at how resistance breaks down. In other words, you've got compound circuits that have both parallel and series, and it's a whole big mess. What we want to do is reduce this down to a simple circuit where everything is just into one total equivalent resistance, and then once we look at the resistances, then we can work backwards. So for this practice, all we're going to do is look at what the resistances do in terms of getting from here to figuring out the equivalent resistance for the entire circuit, and then the next problem we'll do that and then take it a step further. So I'll make this a little bit bigger. And what we're looking for is the total resistance of the circuit. So what happened here, and usually you're going to be drawing these, this was already drawn out. I'm going to circle what everything became. So these parallel circuits here resistors became that. These parallel resistors became that one. These series resistors combined into that one, and these series resistors combined here. So looking at equivalent resistance, we know that parallel, so resistance in parallel, the equivalent resistance in parallel, so 1 over that equals 1 over R1 plus 1 over R2 plus however many resistors you have. So 1/10 plus 1/10, and then the reciprocal of that is 5 ohms. Next we have 1/4 plus 1/8, and the reciprocal of that, that's 2.6 repeated, so let's round that to about 2.7 ohms. These ones are easy, they're in series, so 5 plus 4 is 9 ohms. And these are also in series, 2.5 plus 3.5 is 6 ohms. All right, let me use a different color. Now what we want to do is reduce this circuit. So we've got these 3 resistors that are in parallel. These become that. This resistor and this resistor are the same, so I'm going to keep this as the 5 ohms. To figure out what these are equal to, again, we're going to do the reciprocals, add them, and then take the reciprocal. So 1 over 2.6 repeated plus 1/9 plus 1/6, that comes out to 1.5 ohms. And the last thing we need to do, these 3 are in series, so these 3 combine to become this one, and this is your equivalent resistance. 5 plus 7 plus 1.5 is 13.5 ohms. So when it's asking for the equivalent resistance or the total resistance, it could say either of those. Our total resistance equals 13.5 ohms. And we found that by reducing the circuit. You want to redraw this every single time. So every step you take in reducing, you need to redraw the circuit, and you want to end up with just one simple battery with the wires and one resistor. Let's do the next one, and this time we're actually going to be drawing it. Doesn't draw it for us. It tells us to find the total resistance. So the first thing I'm going to do is combine my parallel resistors. So we're going to end up with this. What happened here, I took those 2 and it became that. I took these 3, which became that. So this resistor is still 18 ohms. For the top one, we have 1/15 plus 1/9. The reciprocal of that is 5.625 ohms. And then over here on the right, we have 1/11 plus 1/5 plus 1/9. Reciprocal is 2.48, keeps on going, ohms. Now we have a series circuit, so we want to reduce that so that we have a simple circuit. So 5.625 plus 2.48 plus 18 gives me 26.1, keeps on going ohms. So my total resistance is about 26.1 ohms. And again, you don't want to worry about sig figs for these because there's going to be so many numbers that you're solving for. All right, so this is how we reduce resistors. Now let's put everything together. In order to analyze the voltage, current, and resistance of the circuits, the first thing you want to do is find the overall or total resistance by breaking it down. So that's what we just did. Once you have the overall resistance, you're already going to know the voltage because that's given in the battery. So we need to figure out the current, and then you're going to go backwards. So when you're going backwards, you're going to be using Ohm's law. So V equals IR, Ohm's law, V equals IR, or I equals V over R to solve for the current and the voltage through each resistor. And you're going to keep going backwards and backwards and backwards until you end up with all of these resistors solved for. So this is going to be long and involved, just a heads up, but we'll get through it, and then we're going to do a bunch of these, so hopefully it starts making sense. And this is the part that's really, it's just a puzzle. Once you figure out how to solve it, it should click, hopefully, and then you'll be able to do these pretty easily. Okay, so I'm going to bring this up and make it a little bit bigger. Okay, let's start by reducing this. So combining what we can, and I'm going to take this step by step by step. First thing I'm going to do is combine these two and these two. And actually, let me not circle this because it's going to get too messy if I'm circling everything. So I'm going to combine these two series and these two that are in parallel. So I need to redraw the circuit. Okay. This is my 100 volts. R1 is still 6 ohms. R3 is 3 ohms. We didn't touch either of those. This was 8 ohms. We added 3 plus 7. So that's 10 ohms. This is still 6 ohms. We did 1/20th plus 1/5 and took the inverse of that, and that gave us 4 ohms. Okay, so now I'm just going to redraw it combining these two. The more steps you take, the better off you are in terms of not making mistakes. Okay, so we've still got 6 ohms. This was 100 volts. 8 ohms. 3 ohms. 10 ohms. And then 6 plus 4 is 10 ohms. Okay, now what I'm going to do is combine the two that are in parallel. So 6 ohms, 100 volts, 8 ohms, 3 ohms, 1/10 plus 1/10, and then the inverse of that, 5 ohms. Now I'm going to combine these two, which are in series. I just redrew that, oops. So we get 100 volts, 6 ohms, 8 ohms, and then 3 plus 5 is 8 ohms. Combining these two, which are in parallel, one eighth plus 1/8, inverse of that, 4 ohms, 6 ohms, 100 volts, and then my last one, we have a simple circuit. 6 plus 4 is 10 ohms and 100 volts. Yes, it should take this many steps because you want to make sure, really, this will be easier working backwards the more times you do this. So now we're looking for the current and voltage through each resistor. I know that my total equivalent resistance is 10 ohms. I know that the total equivalent resistance through this 100 with this 100 volt battery and the 10 ohm resistor can give me a current, and my current is equal to voltage over resistance, so 100 volts over 10 ohms, so my total current is equal to 10 amps. So how do I do this? I write the voltage and the current underneath every single resistor, and then I work backwards. So I know that this 10 ohm resistor has 10 amps of current and 100 volts. Now I use my voltage and current rules through series or parallel. Current is the same in series, so that means now moving backwards that there's 10 amps of current through each of these two resistors. Now I find voltage. V equals IR. So 6 times 10 is 60 volts. 4 times 10 is 40 volts. Voltage should add up, so 60 plus 40 equals 100. So that makes sense. Now working backwards. That's all we're going to do is keep working backwards. These two resistors were in parallel. These two combine to form this 4 ohm resistor. Parallel resistors have equal voltage. So this is 40 volts and 40 volts. The 6 ohm resistor is still 60 volts and 10 amps. We need to figure out what the amps are for each of these resistors. So I equals V over R, so 40 divided by 8 equals 5 amps. And again, these are equal, so this is also 5 amps. My current rules. Going into a junction, my current splits. So there's 10 amps going into this junction, it splits into 5 plus 5. You still have 40 and 40, so parallel resistors have equal voltage. That 40 plus the 60 equals 100. Okay, moving even further backwards. My 6 ohm resistor, these are the same, so 60 volts and 10 amps. My 8 ohm resistor is 40 volts and 5 amps. This 8 ohm resistor was combined 3 and 5 in series. So series resistors have equal current, so 5 amps and 5 amps. Voltage equals current times resistance, so 5 times 3 is 15 volts. 5 times 5 is 25 volts. Here we had 40 volts. 15 plus 25 equals that 40 volts. Okay, these two resistors were in parallel. They became this resistor. So that means that each of these have the same voltage. So 25 volts, 25 volts. Their current is equal to V over R. So 25 divided by 10, 2.5 amps and 2.5 amps. The 3 ohm resistor is the same. So this is 15 volts and 5 amps. Again, checking the current rules, you had 5 amps going into this junction, split into 2.5 and 2.5. My 6 ohms is still 60 volts and 10 amps. My 8 ohm is 40 volts and 5 amps. Okay, this came from these two combining. Everything else is the same as it was here. So we've got, I'm just going to rewrite the ones we know. 10 amps, 60 volts, 40 volts, 5 amps, 5 amps, 15 volts, 2.5 amps, 25 volts. Same current through series circuits, so these are both 2.5 amps and 2.5 amps. Voltage equals voltage equals IV. I can't talk today. Voltage equals IR, so 4 times 2.5, this is 10 volts, and 2.5 times 6 is 15 volts. Well, 15 plus 10 equals 25, so that's where this 25 split between 15 and 10. Okay, almost done. These two were in parallel, so just combining that, they have the same voltage. So this will be 10 volts, 10 volts. This is still 15 volts, 2.5 amps. That's an A. I equals V over R, so 10 divided by 20 is 0.5 amps. 10 divided by 5 is 2 amps. Now we need to look at the 10 ohms here that came from the 3 and the 7 ohm resistors. So we have a 2.5 amp current, 2.5 amps here, and then 3 times 2.5 to get the voltage. So 7.5 volts, and 7 times 2.5 to get the voltage here, 17.5 volts. The 8 ohm resistor is the same, so this is the same as this resistor. 40 volts and 5 amps. The 3 ohm resistor is 15 volts and 5 amps. And finally, that 6 ohm resistor was 60 volts and 10 amps. This is a giant problem. It looks messy, but you kind of need to do every single step. So how do we check to make sure that it's correct? And I'll write everything at the end. But how do we check to make sure everything's correct? Let's look at the rules that we know. So the loop rule. Voltage in a loop needs to add up. We have 100 volts here. 60 volts plus 40 volts equals 100 volts. Okay, and then current gets split at a junction. So 10 amps going into this junction equals 5 amps plus 5 amps. Let's just keep going with the current. So 5 amps going into this junction splits into 2.5 amps and 2.5 amps. 2.5 amps coming into this junction splits into 2 amps and 0.5 amps. So all of my currents are splitting and adding. 2 plus 0.5 is 2.5. 2.5 plus 2.5 is 5. 5 plus 5 is 10. And then knowing that in a series, the amps are equal. The current is equal. So these are both 2.5 amps. And then that's actually the only series there. And then looking at our voltages. So voltages need to add up in a loop. We've got 60 volts here. Here we have 40, and then this 40 goes in, so that means that 40 volts here, these should add up to 40 volts. 17.5 plus 7.5 is 25, plus 15 gives us 40 volts. And then over here we've got 15 plus 10, so that's 25, which equals the 25 volts in parallel here. So everything is adding up. If you mess up early, you're going to mess up everywhere, which is why you really, really, really need to go down to the basics and take every single step. So I broke this apart, 1, 2, 3, 4, 5, 6 times to reduce the circuit. You want to take all of those steps. So our final answer, and I guess I'll make this smaller so I can fit everything. Our final answer, it wanted the current and voltage through each resistor. So this is how I usually write the answers. R1, R2, R3, R4, R5, R6, R7, and R8. And again, we don't want to worry about sig figs. So looking for the current and the voltage. R1, current equaled 10 amps, voltage equaled 60 volts. R2, current was 5 amps, voltage is 40 volts. R3, we have 5 amps and 15 volts. R4, 2.5 amps and 7.5 volts. R5, 2.5 amps, 17.5 volts. R6, 2.5 amps, 15 volts. R7, 2 amps, 10 volts, and R8, 0.5 amps and 10 volts. Yes, these circuits usually do take about this long to do. You need to take all the steps and you need to be careful. There's no trick or shortcut for any of these. So if you feel comfortable with this, then you're good. I will make a separate video if you want to see another example. So sorry for this being so long, but again, you need to know how to do these. You need to pay attention and you need to take your time and take all the steps. So I'll make another video and post that with an additional example. You don't have to watch that if you don't want to.